This is the second lesson in this course on fluid mechanics in medicine. The topic is Archimedes' principle and buoyancy. The learning objective is to apply Archimedes' principle to understand how the buoyant force affects objects that are partially or completely submerged in a fluid. Archimedes' principle, named after the ancient Greek mathematician who, according to legend, discovered it while getting into a bathtub, states that any object, wholly or partially immersed in fluid, is buoyed up by a force equal to the weight of the fluid displaced by the object. What exactly does this mean? Imagine a glass or tank of water into which some object is fully submerged. One of the two major forces acting on that object is the force of gravity, pulling it downward, which we call its weight. You may recall from classical mechanics that the weight of an object is equal to its mass times little g, which is equal to the acceleration due to gravity as measured at the surface of the Earth. The other major force acting on the object is its buoyancy, or the buoyant force, which pushes it upwards. The buoyant force is equal to the density of the fluid times the volume of the fluid displaced by the object times g. Whether or not an object sinks or floats depends upon the balance between weight and buoyancy. Neutral buoyancy is a special situation in which an object's density is equal to the density of the displaced fluid. In other words, its weight is equal to the buoyant force. As you might expect, in this circumstance, the object may seem to hover within the fluid. Let's look at an example of using buoyancy to solve a physical problem. What acceleration will a completely submerged object experience if its density is 3 times that of the fluid into which it is submerged? So density of the object equals 3 times density fluid. From classical mechanics, we know that the sum of the forces acting on an object will be equal to the mass of the object times its acceleration due to those forces. The forces here are its weight, which will be partially counterbalanced by its buoyancy. As previously stated, the weight of the object is its mass times g, and the buoyancy is the density of the fluid times the volume of displaced fluid, in this case the same as the volume of the object times g. We know from the last lesson on density that the density of an object is equal to the mass divided by its volume. So therefore, the mass of an object is equal to the density times volume. And remember that the density of this object is 3 times the density of the fluid. So for each mass of the object, we can substitute 3 times density of fluid times volume of object, which results in this. The density of the fluid is present in every term, so it cancels out, and the volume of the object also cancels out. This leaves us with 3g minus g equals 3 times the acceleration of the object. Solving for a, we find that it's 2/3 g, and of course g is a constant that's equal to 9.8 meters per second squared, which results in an acceleration of 6.5 meters per second squared. This solution is interesting because it highlights that the acceleration of a submerged object is only dependent upon the relative densities between the fluid and object, and is independent of the object's mass and volume. Let's look at another example. Imagine we have an open wooden crate floating on the water, and for some reason we want to put our collection of Michelangelo's David replicas into it. How many 2-kilogram David replicas can be placed into the open 30-liter crate that it itself is 10 kilograms in mass without the crate sinking?